Welcome to another Explainer. I'm absolutely thrilled you're joining me today because we're about to go on this really high-energy journey straight into the fascinating world of electromagnetism. We're going to look at something that, honestly, sounds like it belongs in a sci-fi movie, but is actually powering the world literally all around you. Today, we're demystifying the anatomy of a superpower. We are going to completely break down and understand the solenoid.
To get us to that superpower status, here's our roadmap for today. First, the magic of coiled wires. Then, inside the solenoid's field. Next, boosting the magnetic strength. That leads us directly into the birth of the electromagnet. And finally, electromagnets versus permanent magnets.
So, I want to start by throwing this question out to you. How does a simple, everyday piece of copper wire actually transform into a powerful magnet? I mean, it kind of seems like magic, right? Well, this connection between electricity and magnetism actually traces all the way back to 1820. A scientist named Hans Christian Ørsted accidentally discovered that a compass needle deflected when he placed it near a metallic wire carrying an electric current. He realized right then and there that electricity and magnetism aren't entirely separate forces at all. They are deeply, intimately connected. And that realization is exactly what makes our whole topic today possible.
Okay, let's dive right into this, starting with Section 1, the magic of coiled wires.
So look, if you just take a straight piece of conducting wire, it produces a relatively weak magnetic field. But what happens if we completely change its geometry? Well, this brings us to the actual definition of a solenoid. A solenoid is a tightly wound, helical coil of insulated copper wire wrapped closely together in the shape of a cylinder. Just think of a common spring you might find inside a clicky ballpoint pen, but, made of wire. And it's absolutely crucial that this wire is insulated, usually with just a thin little plastic coating, so the current actually flows through the entire length of the coil, rather than just short-circuiting and jumping across the touching metals. And we want these loops wound tightly, right smack next to each other, so it forms that perfect, hollow, cylindrical shape.
But a piece of wire is just a piece of wire until we pump electricity through it. Let's step into Section 2, inside the solenoid's field.
Now, what's really interesting here is how this magnetic field completely mirrors something you've probably played with since childhood, a standard bar magnet. See, when we pass an electric current through our solenoid, it doesn't just create this random mess of magnetic energy. No, it organizes into a highly structured pattern. The loops of wire work together, and one end of our cylinder actually becomes a magnetic north pole, while the exact opposite end becomes a magnetic south pole. You can see the field lines looping out from the north and curving right back around into the south. We've effectively created an electric bar magnet just by coiling up a wire.
But the real magic of a solenoid isn't just what's happening on the outside. Inside the hollow center of that cylinder, the magnetic field lines are totally different. They don't curve at all. They form parallel, straight lines. Now, in physics, when field lines are perfectly straight and parallel, it means the magnetic field is uniform. The magnetic strength is exactly the same at all points inside that coil. It's perfectly balanced. This creates a really stable, highly controlled environment of magnetic energy right in the dead center of our device.
So how do we take this uniform field and make it even stronger? Let's look at Section 3, boosting the magnetic strength. There are exactly 3 primary ways we can exponentially multiply the magnetic force of our solenoid. First up, we increase the number of turns in the coil. Because the current in each circular turn is flowing in the exact same direction, the magnetic field from each individual loop adds up. 10 turns gives you 10 times the field. 100 turns gives you 100 times the field. It's that simple. Second, we can just increase the strength of the current flowing through the wire. Basically, more juice equals more magnetic muscle. And third, and arguably the most impactful way, we change the core material. Right now, our solenoid just has empty air inside it. But if we put something else in there, well, everything changes.
Let's see how this builds right into Section 4, birth of the electromagnet. That third method of boosting power I just mentioned, here's the secret ingredient, a soft iron core. If we take our hollow solenoid and we slip a solid rod of soft iron directly inside that uniform magnetic field, the solenoid gets incredible superpowers. The magnetic field of the coil actually magnetizes the iron rod itself. So now the iron rod is adding its own massive magnetic strength to the field that's already being produced by the wire. This whole combination of the current-carrying coil and the magnetized soft iron core inside it, this creates what we call an electromagnet.
So the crucial point here is why we specifically use soft iron. Soft iron has this very unique property. It becomes incredibly strongly magnetized while the electric current is flowing, but
And here's the kicker. It loses almost all of that magnetism the absolute second the current stops. It doesn't hold on to it, it's not permanent, it is completely 100% obedient to the electric switch.
And this perfect obedience leads us perfectly into Section 5, electromagnets versus permanent magnets. This really brilliantly illustrates the massive advantage of what we've just built. Let's think about the permanent magnet first. You know, like a classic bar magnet or the one stuck to your fridge. Its strength is fixed. You can't make it stronger or weaker. Its poles are fixed. North is always going to be north. And it is permanent. You can't just turn it off. Now look at the electromagnet we just made. It is incredibly dynamic. We can actually vary its strength just by turning a dial to change the electric current. We can instantly reverse its north and south poles simply by changing the direction the current flows through the wire. And best of all, it's temporary. We can turn a massive, heavy-lifting magnetic field on and off with the literal flick of a switch. It is a fully controllable precision tool.
It's that absolute control that makes the solenoid, and by extension the electromagnet, one of the most important foundations of modern technology. So, as we wrap up this explainer, I want to leave you with this final, somewhat provocative thought. Take a look around your room right now. Which everyday devices are secretly relying on these coiled wires to function right this second? From the speakers playing your music, to the hard drive in your computer, to the little motors inside your household appliances, you are surrounded by hidden superpowers, and they all start with a simple, tightly wound piece of copper wire. Thanks so much for joining me to demystify the solenoid, and hey, keep an eye out for those invisible forces powering your world.